people are filing in, we'll just introduce Brian Boulmay and Mansour Raad from Esri. Brian and Mansour are going to be discussing the science of where unlocking data's full potential. So I'll hand over to Brian and Mansour, and if you can just introduce yourselves and give some context to the presentation and get started. So over to you guys.
Excellent, thank you. Good morning, everybody. My name is Brian Boulmay. I look after the petroleum industry here at Esri, and I'm joined by Mansour Raad, who is our Chief Global Technologist for AI. So we are with Esri. We really thank you for joining us. Today, we want to focus on the value of the spatial component of your data, especially as you apply machine learning and deep learning processes across a variety of workflows. So to start out with a little bit about who we are, some of you may not be familiar with Esri. We are the global leader in the geospatial technology. Our headquarters is in Redlands, California, but we have additional offices across the US and around the world. We've been in business a little over 50 years. We have a very broad customer base, military, government, and the private sector. We work hard to stay at the forefront of geospatial technology. We actually reinvest 30% of our revenue every year back into R&D. It's one of the highest R&D reinvestment percentages across the tech industry. So what do? Our mission at Esri is to develop and deliver the most powerful mapping and spatial analytics software. Over the years, we've transitioned this entire platform of tools to countless times across many different development patterns and technologies. These are constantly evolving and we have to stay on top of it. As we apply and add new capabilities for the customers, we go into these new platforms. At the moment, that's cloud native, and of course, machine learning and deep learning. Today is to give you a bit more insight specifically on machine learning and deep learning in our technology stack. Our platform is also open, so it's very easy to integrate this stack with other analytics tools and even open source technologies. So why do we do it? We do this because we truly believe that location intelligence and analytics unlocks value in your data that you may not be using today to really get to that data's full potential. In the energy domain, so much of what we do is inherently spatial. From where do we drill that next well? How do we route a new pipeline? How do we move refined products around the world? Where do we put our next retail site? All of these processes require spatial questions, spatial analytics, and spatial answers. We recognize actually most of the operators here on the call today are already existing Esri customers. Many of you are enterprise level customers. But with that, we're conscious that often the geospatial teams and the data science teams, they may not be connected in your organizations. And if you're not talking to those teams, you may not be aware that you have some of these tools and technologies you're going to see today. So we really encourage you to reach out to those teams, learn a bit about what they're doing, get access to the technology you already have, leverage their skills, and of course, see the data assets that many of your companies are already managing, and they're available for you to apply some of these techniques to. So with that, we really want to jump into the technology. That's the point of today. As mentioned, I'm joined by our Global Chief Technologist, Mansour Raad. He's going to do a little framing of how the machine learning and deep learning plugs into our technology stack. And then he's going to dive into real world practical examples that we hope will help inspire you to go out and try some of these techniques with your data. So with that, Mansour.
Yes, thank you. Thank you. So I think it's important to first frame the difference between AI, machine learning, and deep learning. I know you all are familiar with this, but again, this circle here kind of encapsulates that separation very well. So as you know, artificial intelligence has to deal with reasoning, planning, knowledge representation, and retaining that information and projecting it forward. And the way to achieve that is through a bunch of machine learning techniques, statistics, mathematics, and there are different modes of operation to be able to achieve that. Unsupervised learning, supervised learning, and of course, one of my favorite one is reinforcement learning. Why things are starting to become so amazing in this world, by the way, of this AI, ML, is this new, it's not actually a new field. Actually, I've been doing deep learning back in 85, 95 when I was still a graduate student, you know. Yes, that's how old I am. And but at the time we could not come up with deep network. And so now with the advent of Moore's law and GPU and stuff like that, there was a resurgence more than a couple of years ago, and deep neural network under machine learning took off. And the kind of results that came out of the using deep learning technique starting to become amazing. And that's what drove this whole new, everybody now is starting to use AI and ML and deep learning, but that separation is very, very important. People do not know something that, by the way, if you have already the ArcGIS software, you've been using machine learning techniques for a long time. So every time you did a classification, a clustering, or a prediction, and you use any of these tools like support vector machine or geographically weighted regression or empirical Bayesian kriging, or anytime you did a multivariate clustering analysis, you've been doing AI and ML, right? Because of the definition that we have. So guess what? You've been doing AI and ML for the longest time. And guess what? With ESRI now, because we constantly keep on adapting over the 50 years we've been in business, guess what? We've added deep learning tools into the equation in here. So again, by the way, these tools can be applied on raster data, like when we want to do here support vector machine for pixel classification. Again, we apply machine learning techniques or deep learning techniques onto imagery. When you do a regression model, this is typically vector-based, like when you do empirical Bayesian kriging or ordinal least square or GWR, that is a form of regression. It is a machine learning technique. And of course, unsupervised learning, which is clustering, again, is a form of machine learning. And when you do a hotspot, you're applying this on, by the way, vector and raster data simultaneously. Again, like I said, what is exciting about this whole thing, and everybody's so excited about, is the deep learning and the neural network that comes into it. And we are now using those new techniques to be able to do pixel classification, for example, to detect buildings and roads, and impervious surface classification. We work with it, for example, like in Abu Dhabi, to be able to detect palms. And by the way, this one came in from drone satellites, and the resolution on these things was so good that we can detect the health of a particular leaf in a particular tree, which is pretty amazing. And of course, the data can be applied to segmentation. And again, just not imagery. In this particular case was LiDAR data that will be extracted. And we applied it in real world scenario, like at the JAIC, the Joint Artificial Intelligence Center, where they wanted to be able to do damage assessment after a hurricane put up an area. And in this particular example, we were able to scale that solution tremendously. Here on the solution here, we use, for example, a Kubernetes cluster of 100 GPUs to be able to scale out that solution to come up with these damage assessment in here. Again, what's exciting about the platform today, by the way, you can do this all in the box today. A full end-to-end deep learning workflow can be done now in ArcGIS in your favorite way. You can use imagery or vector, doing the labeling, data preparation. And by the way, when you want to do the training, you can do it in a toolbox, or if you're a geek like me, you can go down to Notebook and start playing in Notebook to do these experiments, which you can bring in other open source projects into it and blend it in and fuse them together. Of course, when you want to do detection, you can do it on the Pro, or you can do it on server, or like what we've done on a full Kubernetes cluster as a solution that we've done in such a way that you can scale these at massive scale to handle these analysis. And of course, what we're excited about the whole thing is you turn that into what we call geo-actionable information at the end that can be deployed on, for example, handheld devices or mobile field application, and it's pretty good. And as I said, I'm boots on the ground. I use these tools every single day for these scenarios in there. And I want to show you some of these use cases in this particular example in here. So a couple of years ago, we experimented with Georgia Power on how to be able to detect broken or contaminated or flashed insulators from electric line. And so, as you can imagine, they fly out and they take pictures, by the way, of all these things in here, and somebody has to come in and label them. And it's very time consuming and very dangerous. But what we did is we actually ended up doing that all in ArcGIS. We were able to bring in the images. Why? Because every image has a geotag. Whoops. Every image has a geotag that is associated with it. And you can now place those on a screen, on a location, on a map. And using ArcGIS, we can do that. And you can see here, I'm doing through a notebook to visualize all that. Now, Georgia Power has about 170,000 miles, 160,000 structures, over 100,000 images. How you want to be able to process all this? We work with our colleagues at the time with IBM Watson to be able to take that information and perform a classification on that. And yep, let me show you here. We use Watson to be able to do that and dynamically call the API. And as the API is being called, we were able to retrieve and visualize directly the broken insulator. And of course, this thing shows up directly on a map. And that was pretty amazing. So as images come in, we train the model. It shows directly of the geotiff where it is, where the insulator is broken, and highlights it automatically on the map as a classification tool. We've used, for example, structure encroachment. Again, this is a project that we did in Egypt, where again, we trained the model to recognize structures. And the beauty about GIS here is we fused the box that we detected where their structures are with the encroachment buffers, and now it's a pure spatial operation that you do on them, and you can take actions on these encroach structures in here. Another project that we work on with the DOTs, but you can project it. I'll give you a projection here analogy to your use case, which is road crack detections. The DOTs specifies very well what a crack looks like, and there's very specific classes to do that. So what we were able to do is we were able to take a GoPro camera, right, and stream this data up to the cloud. In this particular case, we did it with Azure, and we were able to take the SME, and he labeled that information in such a way that now from the GoPro camera, you can now stream the data and automatically classify where these various cracks are. Imagine in this case where you'll be able to do this to be able to detect improved road or unimproved road dynamically. And now the cost of where you're traveling based on the simple GoPro camera, you will have different costs of operation based on improved or unimproved roads detection automatically. Again, you do not have to go crazy. In this particular case, a simple GoPro camera was able to do the collection, and then by training the model, for example, on what is a improved road versus unimproved road, and tell you where exactly those locations are, you can have a better operating cost for this whole thing in there. Finally, the last project I want to talk to you guys about, which has to do with safety and operational efficiency. An oil and gas company, like some of you guys have, has bunch of oil wells all over the place. And what they want to do is they want to be able to perform inspection on all these oil wells. And typically we do that using network analysts that will come up with the correct sequencing for that. But the problem with that is a lot of these lease roads are not typically digitized in the data that we end up getting. So what you have to do is you have to manually digitize this, and this is very time consuming. And to be able to come up with the best sequencing of stops to do that. And why you want to do that efficient sequencing is, one, to reduce windshield time, right? So like that, people are not traveling as much. And two, operational efficiency when it comes to the best way to most effectively go from one place to another one. However, a lot of you guys maintain a GPS breadcrumb from where the data is coming from, right? And if you look at this, you're like, wait a minute, from these GPS breadcrumb, I can infer roads. And that's exactly what we did. We taught a machine on how to take GPS breadcrumbs and through unsupervised mode of learning, turn them into line features, right? And this is the learning process that you're seeing here in action. And it's very cool as it takes breadcrumbs and turn them into line features automatically for you. And of course, connects them to the network in such a way that now you have a fully navigatable network. And now when it comes down to operational efficiency, yes, now I can know what sequence of oil well pads to go to, right? Reducing windshield time, right? The less somebody is behind the windshield, the more secure it is. And now it is more efficient about the steps that they're gonna be doing, which is pretty cool. And you can do this on not just from GPS breadcrumbs, but also from imagery. So for example, on the left-hand side, this is an oil pad detection model using an SSD, a single shot detection model with the ResNet 18 backbone. And again, we can do it. We did like a full road extraction from imagery here, where we used like, for example, a deep lab pixel classifier with a ResNet 152 backbone. And by the way, for the geeks in the room like me, if you're interested in how we did this, there's a full description about it that shows how we did this in this particular example using the Arcgis API for Python. We will go into the details of the pixel segmentation, what does the model look like, what is the notebook will look like, what kind of Conda environment that you're going to be installing. By the way, a lot of this now comes in, I'm going to show you, easily done, but if you want to get down and dirty and see what it looks like, you can do it. You can do all the installation yourselves. We go into the connectivity to the big data to retrieve it, how you prepare the samples, what did they look like, do you export the data to see what the batches look like, especially with the labels. We have various models to train. In this particular case, I use a very simple shot detector with a ResNet 18 model. We show you what it will look like and what it will take to configure it, what is the backbone will look like, what there is the receptor field, what are the grid sizes that come along with it. We described all that for you. You can learn all about it. And once you have an instance in here, you can come up with the learning rate. Again, this is something very hard for people to detect what it is. We help you find that learning rate. Typically is that inflection point here where it is. And then finally you train it, you give it the number of epochs. This is the slice for the learning rate. And after it learns, you can visualize the ground truth, the prediction model to see what it looks like. You can save the model, publish it, and now you can start using it for prediction on new images and turn these into feature classes that you can operate on that. Again, I know I went a little bit too fast on this, but if you want to learn from all these details, by the way, all these available are on our URLs that I'm going to be showing here in a little bit at the end. But again, you can operate this on AWS, Azure, Google, IBM. There's a lot of tools in the box that you can just push buttons and get going very quickly. You can download pre-trained models, as I said, to do road and building detection. I'm going to show you URL where you can download all this. And if you want to program it, pick your favorite language, Python, R, Java.NET, bring it down, start experimenting with that at the bottom level, like I showed you in the previous here. And when it comes down to connecting data, S3, BigQuery, Cosmos, it doesn't matter. So you have the best of world from everybody in here. So again, these are the references for you all to come down, download, try out. And if you have any questions, Brian, back to you.
Great, Mansour. Thank you. Obviously, you can see his energy and his interest in this. He loves it. So good thing they're recording this so you can play the video back at half speed and maybe keep up with him. So really appreciate y'all joining us. Hopefully we spurred some ideas. I mean, it's really unlimited, right? What if you took those GPS points? Most of you already have IVMS systems in your maintenance trucks. You already have this data in your company. You take those points, you generate the road network. With that, you get the more efficient route. With that, you're getting your maintenance work better planned. But what if you actually use that to start being predictive, right? So start looking at the amount of traffic on your roads. Look at that traffic against weather conditions so that you see changes in the road, so that you're actually sending out your road repair and maintenance people to more targeted locations. So you can take this data and just over and over ask it more questions. And when you add the location element and mix it with other information like weather, there's just really the sky's the limit of what you can do with it. So again, we encourage you, reach out to your internal teams. You have all of this tech, all the operators that we saw speaking, you have this tech. Go out, get the data they have and start running it today. These reference links here that Mansour's provided, a lot of these pre-trained models are already available, so you can just start playing with those. You can build your own, and there's a lot of demos out there you can use for even more ideas. So with that, we wanted to leave 5 to 10 minutes for questions, and we're spot on for that. So I want to open the floor to any questions.
Okay, so we have a question there. Can you see that? Or
Yep.
I can read it. Yep.
So I got it. Can we use ArcGIS for pipeline? Oh, it just disappeared. For pipeline welding inspection. So to me, that would be very similar to the situation you saw with the electric lines inspection. So if you're getting pictures of that, you can absolutely run your machine learning against that. But probably one of the more interesting things you could do is use the same data you're collecting for your HCA analysis. So your soil conditions, your transmission areas, bring all that information together and maybe even target where your crew should go and take those pictures. So you're expanding on the question, need 360-degree inspection of a weld. If you're just interested in single welds, you can do that with lots of different tech. If those welds are geo-referenced, obviously Esri can play in that, but I imagine, Mansour, I don't know if you want to add to that.
Yeah, we work with both, by the way, which is kind of interesting, and we use kind of LiDAR data. Listen, it's very simple. As long as if you have the image, and in the image, you can detect, you as a human, the thing that you're looking for, and you can kind of put a box around it, or you can make a polygon out of it, right? Then the machine can correlate between the two. And the more you have of those, the better it will learn. See, the problem is not the detection problem. The problem is labeling the data and having enough sample to train the machine for that. And that is actually the challenge that we see all the time, is the state of the art that we have, the state of the art of the computational power is very, very good right now, okay? It's very advanced. The problem, what they always see is data, especially for your use cases, what you're trying to detect or stuff like that. That is more the challenge than actually the technology, right? So we work with 360 data, like what Brian is saying. Various other data like LiDAR can help also, again, depending on the resolution of the data, what you can get with it. But, or a fusion, by the way, of those two together can do something for you very interesting. Okay, we use SARS data in some other cases when we're doing oil detection, slick oil detection in the middle of the ocean. Again, could not be detected from RGB, but the SARS picked it up. So various sensors can come in to help you with that. And again, vector or raster or combination of both.
And we also did some work in a previous role where we were doing subsea work with all the inspection video we have for the years, plus new inspections we were doing, and using that content to help drive looking for defects and looking for issues. Maybe not down at a specific weld quality level, but absolutely looking for areas that we need to go back and inspect further along the pipe.
Right.
Do you see the questions in Q&A as well?
I've just seen the one question so far.
Okay, so under Q&A, we also have, do you see value in inference at the edge versus at the cloud?
Definitely. And actually, we're working with some of our partners where they are putting on the edges those GPUs, for example, where the sensor is now hooked in directly to the local processing on the edge rather than pushing it all the way up and coming back down again for a lot of reasons. You can imagine disconnectivity, resiliency to failure, but more importantly, why do that round trip all the way up to the cloud? And this is what they call, some of these people call it like fog computing, right? Like what's a fog? It's a cloud on the ground, right? So they're taking the cloud technology, encapsulating it in these little quote unquote hardened boxes and putting it at the edges. They can operate by themselves or interconnected with each other. We see a lot of that in there. However, this is done on inferencing only, which is the kind of like, if you look at my pipeline, the last stages, we still do the training up in the cloud because of the resources that are available, because of, I can spin up, like, as I said, 2-3 machines to do the training, because again, the training data could be very big. But the model itself at the end, once it trained, the fact that I can push it down to the edge and let the edge operate on it has tremendous value. So that the combination of both up and down, right, is a very powerful combination that you should really capitalize on for various. Processing, and not just again for machine learning, for other IoT and big data processing. And again, now with the miniaturization, you can do so much at the edge. And we're working with that with some of our partners to do that, to like in our case, push GIS to the edge and taking advantage of quote unquote local processing and do more with those sensors that are coming in. Yes, definitely.
So I'll take the next question. It says, could the service path sequence depend on where the driver currently is, then create an optimal path and also determine where they need to be? And this one, absolutely. So doing basic network routing has been there for years. Now with the mobile tools we have available, and these connect directly to the kit, you can have the drivers getting dynamic updates to their path based on what's going on throughout the day. So if a new problem arises and you redirect one of your workers to go to a different location, that then automatically rebalances all your workers' paths so that everybody still gets in an 8-hour day. And so it'll optimize throughout the day, and they're running that list right off of the mobile device in their vehicle. And so that can be done automatically, and that can also be done with human input. And it's a big use case for the Esri stack, and we see that quite often. The next question, I'll throw back to you, Mansour. Do you see hardware, detector sensors, satellites, et cetera, advancements and innovations keeping pace with those you have been describing in the software and computing environments?
So we can take practically any, listen, an input is an input to these models and stuff like that. So there's various inputs that are coming in right now that we can consume or blend together. And if there's one deficient in one, we can complement it with the other one, or sometimes we mutate it to come up with the input, with the different input to the model. Like, for example, I was working with locating things in the desert. Well, when you take the RGB value, it's not good enough, but when you change the contrast and stuff like that, you get better information. And so passing in the contrasted version of that input helps out a lot, despite by the regular eye, you're not seeing that information. So I'm seeing better data coming in and more available and more frequent. And so the combination of the two is, again, deadly, right? But again, it all comes down to data, like what we all know. Technology is good with that data, and without, again, labeling it, you're still not going to get anywhere fast, right? This is very important.
Back to you, Simon.
Great. Thank you very much, Brian Mansour. A great presentation, a lot of interest from the audience. Really appreciate it. On that final slide there, there's some references that you can go to. You can also visit the stand and contact Brian directly. Brian's details are there. So, Brian Mansour, thank you very much. Really appreciated that. And the next presentation actually starts in 3 minutes' time, so you can head on over to the next room. Thank you.
Thank you, everybody.